So today I'll be talking about a statistical estimation problem. I'll be talking about a statistical estimation problem and how we use geodesic convexity and optimization to solve it, right? So this is joint work with Cole Franks and Raphael, who are here, and then Michael Walter, to organize the thing, but unfortunately cannot be here. Cool. So the plan is I will slowly introduce some of the words in the title, and then I will very briefly discuss proof techniques. So if you guys have questions on proof techniques, I am very open to. I think I've left time at the end to ask about that. But no statistical background is necessary to understand this talk, so I'll go through what these problems are, and then I'll discuss the specific problem we'll be solving, which is the matrix and tensor normal model. Cool. So we'll start with what is statistical estimation. Is we're given a bunch of samples from an unknown distribution, and we want to estimate some concrete property of that distribution. Right, so that's the general framework. And also in the general framework, you're given a model. So a model is the family of distributions where the unknown distribution could come from, right? So you don't know everything about the distribution, but you might know something about it, right? And so the running example that we'll be using over and over is the Gaussian model. So you're given a centered Gaussian and unknown covariance, right? I'm gonna use theta inverse for some unnecessary technical conditions, so don't worry about that so much. But the point is you don't know the covariance, but you know something about the family of distributions. And now given samples from that distribution, you want to estimate theta, right? So does anyone have any ideas for a reasonable estimator? Sorry? Yeah, cool. Empirical covariance in this case is like sort of the only thing I can think of, right? It's like the most reasonable and most straightforward thing to do. Turns out it's also a very good estimator, and I'll like quantify what I mean by good. But the point is, in this example, it's clear what to do. In general, it's not clear what a good estimator is. Cool. Or even what good means, right? But yeah, this is sort of the best known estimator for Gaussian covariance. Now we'll discuss, here's a recipe for coming up with estimators, right? So you're given a statistical estimation problem. And let's say you guessed that theta was the true distribution, right? So if theta was the true distribution, then you can look at a PDF of this distribution and measure how likely the samples were. So using the PDF, you say like, how likely was I to come up with exactly these samples? And if that number is small, then theta's sort of a bad guess, right? Like it's unlikely that you saw these if that was the truth. So like flipping that around, the maximum likelihood estimator is you output the estimator that maximizes the likelihood. So you use the PDF as a likelihood measure, and then you pick the thing that maximizes it. So this is an optimization framework for estimation, right? Once again, it's not clear what good means. This is not super important. This is just a bit of a reframing. This will show up later in the problem that we solved. Just notice that this is linear in the first term, so it's easy peasy, and this is convex. So like this is a totally doable optimization problem. And in general, this gives a recipe to find some estimator. It's not clear that the optimizer exists or how good it is, but in our case, it'll be useful. Cool, is everyone clear on maximum likelihood estimation? Yeah, the best part about this is you can actually just solve this equation. You can like set the derivative to 0, and the inverse covariance just pops out. So like we have formally derived why we came up with that very reasonable estimator. It is the solution to this optimization problem. Cool. Okay, now we have some estimator. How do we measure if it's a good estimator, right? And so that depends on the application. That depends on like what properties of the error you care about. In our case, we're going to use this relative error. I'll give some reasons for that later, but intuitively, this is like a multiplicative error. So the relative error between A and B tells you like B is within 1 plus minus epsilon times A, something like that. This thing comes up in like Laplacian solvers and linear system solvers, that kind of stuff. Any questions? Cool. And we'll use these two different norms, so either a Frobenius norm or operator norm. It's important to note this is some sort of like invariant measure. So it only depends on B to the minus half, A, B to the minus half. That'll be more useful when we look at it in terms of like the positive definite manifold. There's some sort of like global invariance that's happening. So it's just measuring, it's going to end up measuring something about the geodesic distance sort of. But just keep in mind the invariance. And then turns out, I won't go through the formulas, but the same is true for this the function that we talked about last time, which the MLE was a solution to. So that function is invariant under this like multiplication on one side. What that means is in order to analyze how good that estimator is in this particular relative error, we can reduce to the case where the input came from the standard Gaussian. So I won't do that formally, but just imagine that there's like a nice invariance on both things that makes it all work out. And that's nice because we can use like awesome concentration properties of the standard Gaussian. And this will come up again when we do our matrix and tensor normal model. But with these reductions, we have this like really classical folklore theorem, follows really cleanly from Gaussian concentration. So it says when ND is bigger than d squared over epsilon squared, you get epsilon error in this sense for the Gaussian covariance estimation problem. I will explain the term up there, right? So on the right-hand side, you have d squared, which is roughly the number of free parameters in the unknown thing, right? So like how many entries does the matrix have is d squared. So you need sort of that many free variables to describe it. On the left side, when you have n samples that are d-dimensional vectors, you're sort of learning nd pieces of information. That's like how I think about it, right? That intuition will again show up in our tensor normal model. But importantly, you sort of need at least d samples to see anything, right? Like if you have less than d samples, you won't even see the whole vector space. So like your error could be entirely off, right? So there's this sort of known lower bound. You can't do better than this. Cool. Yeah, the proof of this is pretty standard for matrix concentration of random Gaussian vectors. Yeah, and this lower bound you should keep in mind for our next problem. Any questions on this analysis so far? So this analysis will be like the gold standard, which we're going to try to measure our next problem by. Like, can we do as good as this? Cool. So our next problem is the matrix and tensor normal model, which is in some sense a generalization of the Gaussian model. So before we describe it, let's pretend that we just have a bunch of random tensors now. So instead of random vectors, we have random tensors. As we learned, like random tensors are just a vector in a larger dimensional space, right? And we learned if these have Gaussian distributions, you need at least as many samples as the big dimension now, which is growing as a product of the little dimensions, right? So that is often quite prohibitively large, right? So let's see if we can think of a good structural assumption, which allows us to bypass this lower bound, right? And so what the model is, this is a matrix and tensor normal model, is you're given a bunch of samples in a tensor space, and then also the covariance matrix respects that tensor product structure. So your covariance matrix is just a tensor product of little PD matrices. Does that make sense? Okay, and then in the output now, you don't just want to estimate the whole covariance, you want to actually estimate the factors. Like now that I know this is a structural assumption, I want to learn something about the factors. This kind of comes up in any application where you can think of a nice factorization of your data. Like you want to learn something about the individual factors. Cool. Yeah, so the two things I could ask for is like, I want the individual factor error to be small, or a weaker ask is the whole thing should be small. But I still want to output something that is a factorization like this. Cool. And now, like with the same sort of logic as before, we have this intuitive lower bound. So notice what is this sum of a d squareds is how many parameters you need to describe the unknown things, right? Each dA sized matrix has dA squared entries. And then on the left side, you're getting n samples of tall d dimensional vectors, right? So that's how many pieces of information you're getting. So this is like what we would aim for to get this kind of sample complexity and similar error to what we got in the Gaussian case. Okay, so now do this first. Sorry, something went wrong in the slides. So I'm going to talk about an example of the matrix normal model and sort of try to explain why this is a generalization of the Gaussian model, right? So in the matrix normal model, you're given a bunch of random matrices, right? And they come from this kind of a distribution. So another way to write that is, I can just write it. So you have xi equals right? So if you have this nice structure on the covariance, another way to say that is you have a random Gaussian matrix, and then you left and right multiply it by some other matrices, right? So a simple factorization. Okay, now that we have these outputs, note that if I knew the right side, right, then this is just estimating the left side is exactly the Gaussian model I was looking at before. A simple way to say that is every column, if you look at it, has covariance that is proportional to theta L, right? So not exactly theta L. And also for that reason, it doesn't concentrate that well, but it's at least proportional to theta L. And if I knew theta R, right, I could just right multiply it. And then all my columns are independent and all my columns are distributed exactly as theta L. So this becomes exactly my like Gaussian model. I'm just estimating theta L using a bunch of independent Gaussian vectors which have covariance theta L. Right, so in some sense, this is harder than just estimating the Gaussian. And now this sort of presents an idea for an algorithm, right? Which is just assume that you know what theta L is for now, and then use the Gaussian idea to estimate theta R, and then go back and forth. So like assume that the theta R is the right thing, and then use the inverse sample covariance to estimate theta L, and then update over and over. Right, so this is the flip-flop algorithm. This was what was suggested early on when this model was proposed. And turns out this is experimentally verified to like converge really well in practice very quickly, even for the tensor case. So in the tensor case, you could imagine I have a tensor, I like assume all my other marginals are correct and fix one, et cetera, et cetera. Right? Cool. Yeah, so I'll go over some previous work now. So the flip-flop algorithm was proposed as this model was proposed as a nice way to think about these distributions that have some factorization structure. And it performs really well in practice, right? It was known to be consistent in the asymptotic case, meaning when the number of samples goes to infinity, the estimator converges to the truth, where the estimator is the thing that the flip-flop algorithm converges to, right? We also don't know what that is at the moment. And then a bunch of other things were known, like we were able to prove rigorous bounds, people were able to prove rigorous bounds on the mean, rigorous bounds on a few low moments, and nice rigorous bounds when you have, for example, sparsity assumptions or some other like structural assumptions on your data. More recently, there's been some algebraic approaches to estimating the threshold when certain estimators exist or are unique, that kind of thing. So this is by, I think Anna Segal will give a talk on this tomorrow. And then Michael and Harm Dirksen and Visu have done some work like exactly estimating this threshold, but no quantitative bounds. So that's what's missing, right? So how do we prove quantitative error guarantees with finite samples with no extra structural assumptions? Like that's what our work is about. Cool, so that's our main result, is in the tensor normal model. This is the only extra constraint that keeps us away from the standard Gaussian case. So we need epsilon to be a little bit extra small. But other than that, exactly the same error as the standard Gaussian case comes out. So for each factor, we get epsilon error when nd is bigger than sum over d squared over epsilon squared, which is like intuitively what you'd expect. Right, so the only thing missing from here is like we have a little bit, this only works when epsilon is small enough. Cool. The other awesome thing is we're able to analyze the flip-flop algorithm using our geodesic convex framework, which I haven't discussed yet, but it turns out that it's a natural descent method in this framework. And so we can analyze why it converges quickly in practice is because of some strong convexity assumptions I'll show later. So this exponential convergence of flip algorithm that we're rigorously able to prove follows pretty naturally from this framework. So the two results say the estimator is good and the flip algorithm converges quickly to the estimator. Cool. So now we can sort of talk about what we do, but in very high level. So feel free to ask questions. Unlike the Gaussian case, it's not clear what our estimator should be, right? In the Gaussian case, there's only sort of one thing to do. Here, it's not so clear. So then we can use the recipe that we talked about at the beginning, right? So we can try to frame it as a likelihood estimation problem. So this is the likelihood function, and we can try to, it ends up you minimize this, which is the same as maximizing the PDF, right? I want to point out now this is not so simple. Like this is not a linear term. There's a bunch of variables. It's not so clear how to do this optimization, but at least the optimization is like well formulated. Cool. And then how do we do this optimization? We're going to relate this to this optimization under symmetry workshop and use geodesic convexity. So this function is really nice. Cool. Yeah, so this is going to be pretty brief, but I'll just discuss how we use geodesic convexity to solve this problem. Okay, so we want to optimize this function over all positive definite matrices, right? And what's natural about positive definite matrices is that there's these very nice geodesic curves on positive definite matrices. One way to think about this is I think about this as interpolating the geometric mean. So it's like thinking of the exponentials and like interpolating those, right? So you have these curves, and then it turns out that our function is convex along these curves. So this follows from sort of the group structure that sits underneath this function. And these geodesics also come from that same group structure. So the geodesics are like naturally derived as shortest path curves based on something about the covariance structure. The other nice thing is that the relative error also relates to this geodesic distance. So I'm able to think about the geodesic convexity to analyze the function, and also to think about the geodesic convexity to analyze like distance in my error. Right? Cool. So this gives me an idea for what to do, right? So I can use this invariance once again to reduce to the identity, just like I did for the Gaussian case. And then I can analyze some simple properties of this function, right? So there's this thing called the geodesic gradient, which is like, what is the regular gradient? It tells me the first order differential at any direction, right? The geodesic gradient is telling me the first order differential along my geodesic curves, right? So I can use Gaussian concentration to show that the geodesic gradient is small, meaning I'm like close to a critical point. And then because I am convex along geodesics, a critical point is also the global optimum, right? So my starting point is close to a critical point, which is also a global optimum. And so I just need to solve for this optimum of this convex function. There has been some work done on these kind of geodesic convex functions in this particular setting, right? By Peter Bergerser and his co-authors, some of whom are here. Unfortunately, these are for worst case results, which require really small initial error and only give kind of poor bounds on the distance. So we'll try to improve that using strong convexity. That's our main plan. And so how do we do this? We can use a really nice result of Pisier to lower bound the Hessian, which is like what strong convexity is, right? So this is like pretty straightforward once you have this nice powerful result of Pisier. So you look at the second order derivative and you lower bound the terms. This allows us to show that the function is geodesically strongly convex, right? Which means maybe we can prove something stronger about distance to optimum and stuff, right? If like the function is curving away from the optimum. And then not only is it strongly convex at the identity, but you can use just sort of term by term analysis on the Hessian to show that the Hessian doesn't change that much in a small ball. So it's strongly convex in a small ball around the starting point, right? Meaning if your initial gradient is small and it's strongly convex near where you are, right, you're going to reach the optimum quickly. That's the idea. Like to do this formally, we need to do beyond worst case analysis of tensor scaling, which is what this ends up being. So tensor scaling is part of the scaling framework that you analyze using this geodesic convex optimization. But once we have that, we have like a nice distance bound for the MLE. Cool. Any questions? Very open to questions to talk about techniques.
Maybe you want to say that like somehow like the more samples you have, like the idea is that the problem becomes kind of more strongly convex, right? That's the idea why kind of these results can hold, right?
Right. So yeah, the way I like to think about it, you very quickly get strong convexity. You have strong convexity, basically like that one condition that I had that makes us different from the Gaussian model, that you don't even need that just to get strong convexity. But in order for your gradient to converge fast enough, you need lots of samples. Like the initial gradient is related to the initial concentration, right? So the more samples you have, the like smaller the initial gradient is. And then you need it to be so small that the strong convexity wins out, sort of, which is why you need that extra condition on that one. But that's what the extra samples help you do, is it shrinks the gradient.
Yeah, I have a question. So for this Gaussian normal model, I think there are identifiability issues. You see that one, see that two, after see that D.
Yeah,
so you multiply by two, some divided by two, but it's the same. How do you handle that?
That's a good question. So in the paper, we just fixed a convention, which is like all the things that equal determinant. Another way to do is to separate the determinant part out. So you take out a scalar factor and make sure these all unit determinant, which fits a little better in the group framework, right? Because now you're optimizing over SL and stuff. Does that make sense?
Sure.
Yeah, it's just a convention. It's not like, I think some people in the literature do different things. And it's just off by scalars. You can sort of guess the scalar at the end.
Okay.
Okay, so now I can talk about some open problems or like what is remaining. Right, so as I suggested, our main theorem is just one dimension factor away from matching the Gaussian model. So it would be nice to remove that constraint. In the paper, we were able to give slightly refined bounds for the matrix normal model, and also like for the tensor normal model, we can decrease the sample complexity a little bit. The second one's my thesis, if you guys are curious. Okay, so that's more directly what the open problems are. And then sort of more generally, there's very simple generalizations of this that we don't know how to do anything for, right? So we suggested, or one suggestion is like, instead of just one product, it's like the sum of two products or K products or whatever. Like none of this framework exactly fits anymore. So it's not clear what to do. Even though that's a pretty natural assumption for your data, right? And then the second one is, as I guess Melanie will talk about later, more general algorithms for like geodesic convex optimization as a whole. Like that's a well-studied and also well-motivated problem from a lot of perspectives. So we used a pretty simple algorithm and simple analyses, but in a very special case, right? So can you think of more general things? Cool, and that's all.
This question here.
Yeah, so it seems like to do the conjecture, you essentially need to say that even though you don't have a locally good initialization, you can say that.
Second?
No, like what's saving you is that with enough samples at your threshold, you can say that the gradient, your initialization will have small gradients, so you converge quickly, right?
Right.
And I presume, but a priori, you could ask for like a worst, like with a smaller sample complexity, you still want to start off farther off, but still argue that you can get which would be true with general convex optimization.
Right, but we don't have enough strong convexity to make it true at that point. Like our
Like
gradient.
you just know it's not true.
Oh no, I don't know.
Oh.
Yeah, I don't know it's not true, and I also don't know that's the only way to go. But that's why our techniques are.
Yeah, I guess maybe you should tell that like there's two theorems, right? Because there's one about the algorithm, and the other one is whether like the MLE can exist. But I think what actually I wanted to say is also that the MLE may exist, but it may not be close to the true distribution.
I see.
Right? So because they're like in this sense, like this theorem doesn't say anything about the algorithm. It's just telling you how close the MLE is to the actual distribution, right? Because if you don't have enough samples, you wouldn't expect with high probability. Exactly, right? So that's what we are able to prove. But yeah.
Any other questions?
Thank you.